Hello, everyone. I'm Alessandro Epasto, and today I'm going to talk about a joint work with Brian Perozzi. I'm part of the graph mining team, and this is about node embeddings. So first of all, what are node embeddings and why do we need them? As you all know, graphs are a discrete data structure. They contain discrete information like nodes and edges, while modern machine learning technologies usually need some continuous input to operate. So for this reason, we use node embeddings or graph embeddings to turn this discrete data structure into a continuous input. And there are many applications for node embeddings, including node classification, edge classification, and link prediction. But today we'll see mostly how node embeddings operate. So let's start with some basic technology. So one of the first node embedding methods developed was deep walk by Brian Perozzi. And the way it works is that it simulates some random walks over the graph. And then it uses these random walks to embed each node in a single position of the space. The way it works is that the random walks are analyzed with a neural network as if they were sentences, where the node IDs are words in these sentences or tokens. By using natural language processing technology, we can then embed each word or each node into a position of the space that depends on the relative position of the node into the sentences, which are the random walk sequences. And this has many applications, as you already know, and it works very well. But today, we're going to address the following question, which is just a single embedding enough, as it is done in deep walk and in the vast majority of other embedding technologies? And the answer, as you can imagine, is that sometimes it's not enough. And one intuition for this is that, as in natural language processing, it's well understood, sometimes the word may have different meanings. Like the word bank may mean both a financial institution and a riverside. So what we observe in our paper is that the same applies for graphs. So the same problem is true of graphs. Nodes may have multiple meanings in the language of a graph, which means that they belong to multiple communities. And so if you use a single embedding to represent them, you may have performances that are lower than if you use multiple embeddings for each node. And this is essentially the general idea of our paper. And today we're going to see how you can actually use an embedding technology that embeds the nodes in multiple positions in the space. And first of all, I want to explain why this may be very important. I want to start with an intuition from random walks. So as we have seen, random walks can be used to embed nodes like in deep walk. But what happens if a node is part of many overlapping communities, like social communities like work and family and friends? So if a node is part of many communities, what happens is that there are many connections that between the inside of the community and the outside world. And if this happens, it means that the random walk starting from a node will cross the boundary of these communities very easily. And when that happens, it means that the random walk will explore the outside of the community more than the inside of the community. And it means that it's hard then to embed the node in a unique position and identify the multiple communities to which the node belongs. This is something that has been already observed for random walks even before the embedding technology started to become prominent. But there is a solution which consists in analyzing, instead of the macroscopic structure of the graph, we can look at the microscopic node-centric structure of the graph. In particular, we can look at ego networks. And what I'm going to show you is that by looking at ego networks, we can actually disentangle these communities to which the node belong. And so this is the idea. So first of all, I want to define what an ego network is. An ego network is a graph theoretic concept which is defined for each individual node in the graph. So for one node, like the center red node in the slide, the ego network is defined as the set of neighbors of this node and all the connections between them. This is sometimes called the ego network minus ego, but I will just say ego network for now on. So why do we care about the ego network? The reason is that by looking at this graph, it may be much simpler to disentangle the communities to which the node belong. Like in this toy example, you can see easily that there are two disjoint subgraphs. So even connected component will be able to identify the family and the work community of this node. While if you look at the entire graph, these two communities are very well connected because there are many connections between them. So this is the general intuition of our paper, and what we show is that if you analyze the ego networks, it's much simpler to disentangle the communities to which the node belong, because there is usually one single context in which one node interact with another node. So now that we have this intuition, what we define is the persona graph, which is a concept we define in a KDD paper. And what we show is that with this graph, which is a new graph concept, you can process a graph and turn it into another graph where these communities are separated. And what I'm going to show you is how to do that in a very efficient and flexible way that has also some theoretical guarantees in terms of graph clustering. So what is the persona graph intuition? As I said, by looking at the ego network of a node, we have identified that this node is part of two communities, right? Family and work. Now that we have identified, for instance, that the node is part of two communities, what we are going to do is that we will replicate this node and create two separate nodes, which we call the persona nodes. And now that we have these two nodes, we will connect each of them to the specific subset of neighbors of the original node, to which this specific persona node is an instantiation of the community of. And so now that you have that, you have that these two nodes essentially have separated these two communities because they are no longer connected, as we don't have anymore a single node, but two nodes. Of course, if a node is part of more than two communities, we will create more than one persona node. And if a node is part of a single community, there would be only one node. This is done automatically by using a graph clustering algorithm at the level of the ego network. So now that I've defined how this graph more or less works, this is the flow. We start with the graph, we analyze the ego networks, we partition them using a non-overlapping clustering algorithm, we create a persona graph, and then we analyze this graph to embed the nodes, and we map the persona nodes to the original graph. So this is in this slide, you can see the overall flow of the analysis. We start with the graph, we perform ego network analysis and create this new graph. Notice that in this new graph, each node may be represented by multiple nodes. So if you embed each node of the persona graph, you can get multiple embeddings for each original node. And since these embeddings may diverge, for some technical reasons, we also use an embedding of the original graph as a regularization, but this is the general flow. As you can see, you get now an embedding where each node may be represented by multiple positions. So here I'm showing you some example of how this works. On the left side, on the top, you can see the original graph. On the left side, on the bottom, you can see the persona graph. And clearly, the persona graph is even visually very simple to analyze. You can see the communities are already like disentangled, just like visually this is obvious. And so it's not surprising that on the right side, you see that our embedding on the bottom, the splitter embeddings, separate these communities much better than the standard embeddings on the top right side, like the node-to-vec embeddings. So this also translates in improved performances in downstream tasks. For instance, in link prediction, we show that we improve over previous results for link prediction. Here, clearly, there is a challenge, which is how do you use many embeddings for one node? And what we show is that even just very simple, not optimized techniques like using the maximum of the dot product of any pair of embedding of a node to define similarity is sufficient to get very good performances. And now is here again another visualization. Without going into details, it's here we show basically that it's clearly in some cases you really need to have multiple embeddings. For instance, this is a co-authorship graph, and I'm highlighting a very popular and very prolific author. And since this author belongs to both the data mining and the information retrieval community, of course, if you embed the author in a single position of the space, it will be the average of these two communities. While with our persona class and persona graph embedding, we can see that the node is represented in multiple locations. So in conclusion, we have seen that using multiple embeddings for one node allows to understand the different meanings of a node in the context of a graph. And this can be used to do link prediction. So as a future work, what we would like to do is to also apply this to node classification. And this is a more challenging task. And we also want to understand better how these meanings of node relate to each other. So thank you very much for your attention.